everyone, welcome back to Chemistry Learner. So today we'll be starting the super important chapter of plus 1 chemistry, thermodynamics. This chapter is not only important for your board examination, it is very important for different competitive examinations like JEE NEET, etc. So we'll start with this chapter. So today I'll be discussing mainly the important terms used in this chapter like system, sink, universe, and also different kinds of system and different kinds of thermodynamic processes and first law of thermodynamics, which is very important, and also few equations and their derivation, and also I'll be solving few numerical problems which will help you to understand the theory as well as how to apply it. This chapter you may feel little tricky, so I'll explain you this very step by step. So listen carefully and take your notes in between wherever it is needed. Okay, so if you have any doubts, please drop your comments and I will reply for sure. And also if you like the video, please like and share it with your friends. So we won't waste our time. Let's start our class. So let's start with the unit 5, thermodynamics of plus 1 chemistry. So thermodynamics, so here we are studying more regarding temperature and the feasibility of a reaction. So first let's familiarize with few important terms which is associated with thermodynamics. So the first one is system, then surroundings, then boundary. These are the three important terms that we need to know. So look at here. So system is anything under observation is called system. So which part of universe we are studying, that part is called the system. So the definition of system is given here. The part of the universe where observations are made. So one thing I will tell you, these things you don't need to take the notes. So there you can take the screenshot, because while I am describing the important terms, first you listen, then you take the notes. That will be more easier. Otherwise you cannot understand the concept. Okay. So don't take the notes now. First you try to understand. Then you can write it down by pausing it. Otherwise, if it is finding difficult for you, you can ask me. I will provide you the notes in the description. Okay. So first we need to know what is system. So system is anything under observation. So the definition is given here. The part of the universe where observations are made. So it can be a one glass of water. It can be some particular gas. Anything. So whatever system we are studying, that is called the system. And surrounding is anything other than system is called surrounding. So one thing we need to know, that is surrounding is actually surrounding meaning is given here. Everything outside the system is universe. Okay. In the universe, whatever is outside the system, that is called the surrounding. So we can see this complete yellow portion is the universe. So inside that there is system, which is the blue colored, which is under the study. Okay. Then outside this whatever is there, that is surroundings. Okay. But one thing we need to know, so entire universe other than system is not affected by the changes taking place in the system. Okay. So that what is meaning by, like if we are taking a glass of water, so whatever changes are happening there, it is not affecting the entire universe. Okay. Other than system, it is not affecting the entire universe. Actually, if we are telling, it is that portion of remaining universe which is in interaction with the system. So it can be that particular room in which that glass of water is staying. Okay. So it is in the neighborhood, whichever. So if we are performing some changes in the system, it will affect some changes in the surroundings also. Okay. So it doesn't mean that it is whole universe. Okay. I am not telling about whole world is a surrounding. Surrounding means it is which is in the neighborhood of the system. So which can interact with the system. Okay. So that is called surrounding. So system and surrounding together called the universe. Okay. System and surroundings, if you are taking the sum, that is called the universe. So this is the total full portion is called the universe. Then one more term is there, boundary. Boundary is anything which is separating between system and surroundings. Suppose, as I told, if you are taking a glass of water, in that glass portion is there, right? That is the boundary which is separating from the water from the remaining portion. Okay. So boundary is the wall separating system from surroundings. Okay. So we understood the definition of boundary also. So there are different kinds of boundaries. It can be real, imaginary, it can be thermally conducting, it can be insulating. So different kinds of boundaries are available. Okay. So three terms are important: system, surroundings and boundary. I hope you understood, because this is the basic. So this is the starting point of your thermodynamics. You should understand these terms, otherwise in future whenever you are describing something you won't understand. So I hope it is clear to you. Okay. So as I told, the system, we can classify the system into different. One is open system and another is, so here it is open system, another is closed system, then one is isolated system. Okay. So open system means there heat transfer and mass transfer is occurring. So we can see here mass is also getting transferred and heat is also getting transferred. So as I told, if you are taking some reactants in an open beaker or open glass of water, that means that if it is hot, after some time that temperature or that heat will get transferred from the glass to the surroundings. Okay. So that heat transfer can occur from inside to outside as well as from outside to inside. At the same time, the mass can also get transferred. It can get vaporized and some quantity of water can go out. So that mass transfer also occur. So such systems are called open system. Then another system is closed system. Closed system means here what is happening is it is closed. You can see here no lid is there. Here one lid is there which is closing the system. So reactants we are taking in a closed vessel. So in that case what is happening is mass transfer won't happen. Here only transfer of heat will happen. Okay, mass is not getting transferred, only heat is getting transferred. Such systems are called closed system. Okay, then another is isolated system. Okay, isolated system means in this case mass transfer also won't happen, heat transfer also won't happen. So suppose we are taking the reactants in a thermos flask. Thermos flask means it will never transfer the heat with the surroundings. So there is no mass transfer, there is no heat transfer. So this kind of, you can see around your room, you can see different kinds of system. Okay, so suppose a cup of tea has been taken and you can see if it is opened there, after some time it can undergo mass transfer also, heat transfer also. Suppose it is closed, then mass transfer won't happen while heat transfer will happen. And suppose if we are taking that tea in some thermos flask, in that case what will happen? No mass transfer, no heat transfer. Such systems are called isolated systems. So these are the three kinds of system. So here what you need to know is you have to know what is happening here, because sometimes in question it won't directly ask you open system, closed system, isolated system what it is. It won't ask the definition. Sometimes some problems may come to calculate it in the open system, or to calculate it in the closed system, or to calculate in the isolated system. So that time you should know what does that mean. Okay. The next term is state variables. So state variables means, as I told, there is a system which is under study. So this is the system. So the thing is that we can identify the state of a system by defining some variables like pressure, volume, temperature, amount of gas. If we are defining these things, we can state the system. We can describe the state of the system. Okay. So here I have written, state of a thermodynamic system is described by measuring some properties like pressure, volume, temperature, amount of gas, etc. So such variables which can define the state of the system are called state variables. Okay. So example is pressure, volume, temperature, etc. So one is state function. State function, in this case, the variables whose values depend only on the initial and final state. So this variables, it will depend, the value only depend on the state of the system, not on how it reached. For example, if we are changing the temperature from T1 to T2. So if we want to calculate the difference in temperature, we are just taking the subtraction T2 minus T1. We don't want to know what is happening in between this. So suppose it is at 10 degrees Celsius, we are increasing it to 20 degrees Celsius. So we know that the temperature difference is 10 degrees Celsius. So we don't want to know in between that whether it increased by 2 degrees Celsius, 3 degrees Celsius, 4 degrees Celsius. We are not concerned about that. This is just state of the system. Okay. It is only depends on the state, not on the path. Suppose if it depends on the path, there are two variables like work and heat. In such case, these are path variable. Okay, path function. Path function means in this case, we cannot simply write delta W equal to W2 minus W1. So this one depends on the path, how it reached. Okay, suppose if we are taking volume. So volume, if we are taking, we can write a delta V equal to V2 minus V1. Suppose there was 1 liter of water, then it increased to 10 liter of water. So there we doesn't care whether it increased by either by pouring water by us or pouring water from tap or pouring water from some pipe. We doesn't care. So we just need to know the difference. Such functions are called state function, while path function means it depends on the path how it reached. So there are two important path function, that is work and heat. Okay. Now, as I told, these state variables, we can define the state of the system. So it is not always mandatory to define pressure, volume, temperature, amount for a particular gas if you are considering a gas. So we don't need to mention all these variables to define the state. Suppose one or two of them are defined, the other will have automatically some definite value. Like once minimum macroscopic properties are fixed, others automatically will have definite value. What does that mean is, suppose for a gas we know ideal gas equation, otherwise you will study. Okay, ideal gas equation is PV equal to nRT. So in this case, if we are defining pressure, volume and number of moles, automatically temperature will get fixed. It will have some definite value. So we don't need to define there. For 1 mole of gas, we just need to define the pressure and volume. So the temperature will be fixed. Otherwise, we just need to define pressure and temperature. That time volume will be fixed. So we don't need to define all these variables. Once some minimum macroscopic properties are fixed, others will automatically have the definite value. That is the meaning. Okay. Let's go to next slide. So next slide is extensive and intensive properties. So this is another important term. Extensive means it depends on the quantity of the matter present. Okay. While intensive means it is independent. It does not depend on the quantity of the matter present. Okay. So this you need to remember. Intensive means you can remember like independent. Okay. Intensive is independent of the amount of the matter. Extensive is dependent on the amount of the matter. For example, you can see mass. Mass, like based on the quantity, it will change. Volume, internal energy, enthalpy, heat capacity, these all things are extensive properties. While temperature won't change if you are taking 1 mole, 2 mole, 3 mole for everything. Temperature won't change with the quantity or size of the matter. Similarly, density. Density, if you are telling density, you know the equation density is equal to mass by volume. So mass is what? Mass is, we know this is extensive property. Then volume is also extensive property. Then, but when we are taking the proportion mass by volume, it will be intensive property. That we need to remember. Okay. Then pressure is also intensive property. So here is an example you can see. So there is a box of gas which is at volume V and temperature T. Then what we are doing is we are splitting this box into two parts. At that time what will happen? The gas inside this part will be having a volume of V by 2 and here also volume will be V by 2. That means volume is getting halved while the temperature will remain constant at both parts. So that means that when the size is reduced, when it is divided into two, size reduced but temperature didn't change. It doesn't depend on the size. So that is intensive. While volume is getting halved. As the volume changes with the mass or size or quantity of the substance, this is called extensive property. Then other thing is molar property. Okay, what is molar property? Molar property means if we are taking some extensive property. Suppose some extensive property chi for 1 mole of substance. So molar property can be defined as chi m is equal to chi by n. Okay, chi m is equal to chi by n. So chi is an extensive property. N is number of molecules, and this also depends on the quantity. Extensive. Taking the ratio of two extensive property, it will be intensive property. That you need to remember. Okay. So remember, whatever molar property you take, suppose molar heat capacity is extensive, but molar heat capacity will be intensive. Similarly, enthalpy is extensive, molar enthalpy will be intensive. So that kind changes will happen. That also you have to remember. Okay. Next one is different types of thermodynamic processes, like isothermal. In isothermal process, temperature remains the constant. Okay, so the temperature do not change. So temperature do not change means we can write like delta T is equal to 0. Next one is isobaric. In this case, pressure remains the constant. That means delta P will be equal to 0. Next one is isochoric. Isochoric means volume remains the constant. That means delta V will be equal to 0. So these things you need to know, because they won't ask you in question whether the temperature is constant or pressure is constant or volume is constant. They will directly ask you calculate these things, either work or heat, for isothermal process, isobaric process, isochoric process. So you need to know what does that mean. So isothermal, thermal, when you are seeing itself, you can remember it is related to temperature. In that case, temperature is constant. Isobaric, bar means it is a unit of pressure. So in this case, pressure is constant. While isochoric means volume is constant. Then another important thermodynamic process is adiabatic. In adiabatic process, no transfer of heat. That means Q, heat is equal to 0. Heat is not getting transferred, heat is not getting entered, like thermos flask. In that case, there is no transfer of heat, like in that isolated system. Okay. While there is another term, cyclic process. Cyclic process means system returns to its initial state after different process. Suppose a system is starting from this position, it is going from X, it is going to Y, it is going to Z, then finally it is returning to X itself. So such process is said to be cyclic process. It starts from one position but it undergoes different process, finally returns to its initial state. Such process are called the cyclic process. Okay. So next one is reversible and irreversible process. A reversible process can be reversed at any moment by infinitesimal change. So this one usually proceeds very slowly through equilibrium states where system and surroundings remain in near equilibrium. So in such state, system and surroundings will be in near equilibrium. So at any point of time, we can change a little bit of some properties so that it can be reversed. While irreversible process occurs much faster. So all processes that are not reversible are called irreversible process. This also you should remember, because as I told already, in questions they will ask you calculate this and that for reversible process. So you need to know what is mean by, what does that mean. Okay, so these are the important terms that we have to use in thermodynamics. Okay, so I'll recap. First I have told you about what is system, surroundings and universe, then boundary, then different kinds of system like open system, closed system, isolated system. After that we have discussed about state variables and path variables, and also about intensive and extensive properties and different kinds of thermodynamic process like isothermal, isobaric, isochoric, and also reversible and irreversible, and also adiabatic process, cyclic process. So these are the important terms that we have to remember. This is the first part. This is the base of thermodynamics. So this much you just revise or take notes, whatever you want. Okay. Then we'll go to the next section, that is internal energy. So internal energy means inside a system there are different molecules. So it will be having some kind of energy. So that energy is called internal energy. But internal energy is actually the total energy of the system. This energy can be chemical, electrical, mechanical, any other form. Whatever be the energy, sum of the total energy. Okay, the total energy is called the internal energy. Okay. So this internal energy will change only when either heat transfer occur or work done happen or matter transfer happen. So in these stages only internal energy will change. That we need to remember. Okay. So let's see what is happening when heat transfer is occurring. When heat is getting passed into the or out of the system. So it is having an internal energy E or U, we can tell whatever it is. Then what I am telling is, suppose to this, sorry, I'll just erase it. So suppose what is happening is, if we are passing some kind of heat like Q we are giving. Okay, suppose we are passing a heat Q to this, or it is releasing some amount of heat to outside. It can happen either way. But in that case there is no work done. Only heat is getting transferred. In that case, internal energy change delta U will be equal to Q. Okay. Then, suppose work is getting done. Either work is done on the system or work is done by the system. Okay, these two things can happen. In that case, delta U will be equal to only work done, but heat is not getting transferred. That is why it will be equal to W adiabatic. It will be conducting at adiabatic condition, because in this case Q is 0, only work is getting done. So that is why it is called delta U is equal to W adiabatic. Change in internal energy means it is equal to work done. Here the change in internal energy is equal to heat transfer. Okay. So here what is happening is, in this case it will be conducting at constant volume, because work done is given by, that we will discuss later how this expression is coming minus P delta V. So this delta V will be equal to 0. That is why W also will be equal to 0. That is why delta U, the change in internal energy, will be equal to Q. Then otherwise matter transfer, matter can enter or leaves the system. That is another way. Okay, so that also we'll see. Either some more matter can enter or matter can leave. In that case also internal energy can change. Okay, these are the three cases where internal energy can change. Now for this work and heat there are some sign convention. So you have to remember one thing. So whenever the internal energy delta U, means delta U is positive, whenever the internal energy increases, in that case what will give? We will give the positive symbol. If the internal energy is decreasing, delta U is negative, then we will give the negative. This is the sign convention that you need to remember. So look, suppose heat is transferred to the system. So we are transferring some amount of heat from here to inside. So suppose heat is getting transferred to the system. In that case what will happen? Internal energy will increase. So in that case we need to give positive sign. So positive, heat is transferred from surroundings to the system. Suppose heat is getting released from the system to the surroundings. In this case what will happen? So since the heat is getting released, internal energy will decrease. So in that case we need to give negative symbol. So negative sign. Okay. Now in the case of work, suppose work is done on the system. When that work is done on the system, what will happen? Internal energy will increase. When we are doing some work on the system, its energy will increase, right? So in that case what will happen? We will give the positive symbol. On the other hand, if it is getting released, so work done, if suppose it is getting released, work is getting released or work is done by the system, so system is doing some work, in that case its energy will reduce. So system is so you can imagine, so if we are the system and we are doing some work, our energy will automatically reduce. and if someone is giving is doing work on us and it is giving energy to us, means energy will increase, but in this case work is done by the system, so internal energy will reduce. So in that case work we will give negative symbol, that is written here. Heat, usually positive sign when heat transferred from surroundings to the system, while negative when heat is transferred from system to the surroundings. While work done, positive is work done on the system, while negative is work done by the system. Okay, so if you cannot remember this, just remember that internal energy, whenever internal energy is increasing, that time you need to give plus sign. When the internal energy decreases, you need to give negative sign. So let's go to next slide. So as I told now, so here we have considered only either change in internal energy by heat or work. So we are not doing at a time both. Suppose if we are doing both at a time we are transferring the heat also, work also. In that case we can write like delta U is equal to Q plus W, because before we have written when heat is not there, that time it is equal to W. When work is not done, that time it is equal to Q. But suppose at a time both are there, means delta U will be equal to Q plus W. This is called first law of thermodynamics, which is very important, that you have to remember this equation, delta U is equal to Q plus W. So the law states that the change in internal energy, so this equation only you need to remember. So the law you can simply define, because the change in internal energy is equal to the heat added plus work done on the system. It is written here. Now suppose this W, work done on the system, is 0. Suppose heat is also 0. In that case delta U also will be equal to 0. If W is 0, Q is 0, then delta U also will be equal to 0. That means the energy of an isolated system. Okay, for an isolated system, there is no heat transfer, there is no work done. In that case, the energy of an isolated system is constant. That means since energy is constant, delta U is equal to 0. So this is another important way of expressing first law of thermodynamics. You might have heard first law of thermodynamics can be in another way. This is also another form. That means energy can neither be created nor be destroyed. It can be transferred from one form to other only. Okay, unless there is no heat, no work, there won't be any energy. It will get transferred from one form to other only. Okay, so this is the first law of thermodynamics. Now we will have a discussion on work. So we have already told that W is equal to, before I have told, I will let you know how this comes. P is equal to minus P, W is equal to minus P delta V. So we should have some more discussion how this is coming. So you can see here is an ideal gas cylinder. So there was a pressure P. Now we are applying an external pressure P external. So when we are applying some pressure, so there was a piston at this position. After some time it will move and it will reach this position. So from here to here the volume also changes. So when it was this much, it was having a volume of Vi, that is the initial volume. Okay, and after some time what will happen? Volume will reduce, that is Vf. It is not visible. This is Vi, this is Vf. After some time when we are applying external pressure, it will reduce to Vf. Okay, so you can see the pressure volume graph. So as the volume varies, pressure means we are applying an external pressure P external, and volume varies. Volume Vi is here, Vf is here. So the difference between these two is this shaded area. So area under this curve, this green shaded area corresponds to W. Okay, so W is equal to P external into delta V. So we should know how this is coming. That I will tell you. Means suppose, let's take like, suppose the volume change, when it is getting changed, the volume change is given by delta V, means it is equal to length into area. volume change we can tell like Vf minus Va, final volume minus initial volume, that is equal to length. Volume can be written as length into breadth into height, that is equal to length into area. Volume can be written like that also. That you already know, that is simple mathematics. Then another thing we need to know is pressure. Pressure is having equation of force per unit area. Pressure is force per unit area. So you can write force as pressure into area. In this case we are applying an external pressure P external into area. So W, we need to know the equation for W. W is equal to, we know from physics, we know force into displacement. In this case displacement means it is getting piston is getting moved from this position to this position, which is marked by L. That is the displacement. So force into displacement is work done. For force we have already written P external into A into length. So A into length is what? A into length is delta V. So we can write like P external into delta V. This way for work this equation is coming, P external into delta V. Here, but one more thing I will tell you, here I will add a negative symbol. Why I am adding this symbol? Because actually work is done on the system. So when work is done on the system, according to sign convention, it should be positive. Okay, when work is done by the system, it is negative. When work is done on the system, it should be positive. So if work has to be positive means, we know delta V is what? Delta V is, you can see Vf minus Va. So Vf is higher or Va is higher? Va is higher. Okay, Va is higher. So when we are subtracting a higher value from a lower value, this delta V will be what? Negative, as Vf is smaller. So this is already negative. Since delta V is negative, to make this whole term positive, we are adding a minus symbol here. So that's why it is becoming minus P external delta V. So this is the equation for work done in the case of an irreversible process. This is one thing I will tell you, this is for irreversible, not for reversible, irreversible. Reversible is coming next. Derivation I will show you in the next, but I will show you what is happening. So here you can see the pressure is not constant. So in this case the pressure was constant throughout the experiment. In this case pressure is not constant. You can see for some point of time pressure was this much, then pressure reduced to this much, then pressure reduced to this much, again pressure reduced to this much, again pressure reduced. So at each step pressure is getting changed. So similarly volume is also getting changed. So the area under this whole curve corresponds to the work. So for this kind of system we can write like it is equal to minus sum of P delta V. So it is P delta V only, but we have to take at each step how much P delta V. For this much fraction how much it is, for this much how much it is, for this much how much it is. Finally we need to add everything. So this is when pressure is not constant and changes happening in finite steps. So suppose it is happening, the pressure is changing in infinite step, like we cannot define, like it is happening continuously. Like here we can see pressure is constant at least for this much time. In this step pressure is changing at infinite steps. Okay, here pressure is changing at finite steps while here pressure is changing at infinite step. When it is changing at infinite step, it is called reversible condition. So this is reversible condition. In such case what to do? So what is the equation that we have to discuss? So in such case we will write like it is the integral of from Vi to Vf P dV, P external dV. dV is the small change in volume happening because of the pressure change. Okay, so minus P P external dV. Then we are integrating it from VI to VF. This is for reversible condition. So this is for reversible, this is for irreversible, this is for pressure change at finite steps. So this one for reversible condition, we should have little more detailed derivation that we will discuss. So as I told, W for reversible, so derivation for reversible I am writing here. We know W is equal to minus integral VI to VF P external dV. Okay. So P external pressure is equal to internal pressure plus dP. dP is the change in pressure. This can be internal pressure if we are doing the compression. It can be plus dP because we are applying some pressure. And in some cases what we will do? Expansion. In that case what pressure? We will release the pressure. In that case pressure will reduce. P internal minus dP in the case of expansion. So both can happen. So together we can write like P external is equal to P internal plus or minus dP. Togetherly we can write. Then this equation we are taking. Okay. So we have to find out W for reversible process, which is already I told it is the integral from VI to VF P external dV. Okay. So we can replace this P external with P internal plus or minus dP into dV. So we should know that, so this one will become like P internal into dV plus or minus dP into dV. So dP into dV. dP is the change in pressure, dV is the change in volume. This both are very low values. So this will be really low, which can be neglected. So this equation will become minus integral of VI to VF P internal dV. Okay. Then I am just erasing here. I am just erasing here so that we can write it here from here. Okay, I am writing upside. As I told, this much we got. So P internal, what is P internal? We need to know. So for an ideal gas, PV equal to nRT for an ideal gas equation. So in that case, P is equal to nRT by V. So we can substitute this ideal gas equation there. So it will become W is equal to minus integral of VI to VF. Instead of P internal, we will substitute with nRT by V dV. So at constant temperature means isothermal condition. So N is number of moles, which will be constant. R is gas constant. Temperature is also constant. These terms will take outside and it will become VI to VF 1 by V dV. When we are integrating 1 by V, we will get ln minus nRT. 1 by V dV integration is ln V from VI to VF. So this one will become minus nRT ln VF by VI. Okay. So this is the final equation. Minus nRT. This is the final equation. Minus nRT ln VF by VI. Otherwise, we can write it in the log form also. Minus nRT ln VF by VI. Otherwise, we can write it in the log form also, which is equal to minus 2.303 nRT log VF by VI. This way also we can write this equation. So this is the important equation for work done in isothermal reversible reaction. Now we will discuss regarding free expansion. So free expansion means it is the expansion of gas into vacuum. Vacuum in the sense there won't be any external pressure, which implies that P external will be equal to 0. Okay, the external pressure will be 0. Such condition is called vacuum. Okay, so in that case, the expansion of gas in vacuum is called free expansion. So, in this case, we know W work done is given by minus P external into delta V. In the case of irreversible, if it is reversible, it will come integral minus P external delta V. Whatever is the case, this P external, when P external is equal to 0, this W will be automatically equal to 0. So, whether it is reversible, irreversible, it doesn't matter. Work done during a free expansion will be equal to 0. That is written here. No work is done during the free expansion of an ideal gas. So, you should know when it is telling that it is a free expansion, their pressure will be equal to 0. External pressure will be equal to 0. Whether the process is reversible or irreversible, there is no work is done. W will be equal to 0. So, for an isothermal and free expansion of an ideal gas, as I told already, when we are seeing free expansion, P external is equal to 0, which implies that W is equal to 0. And also, Joule determined experimentally that Q also will be equal to 0. Heat, there won't be any transfer of heat also during such free expansion. So, we can write according to first law of thermodynamics, delta U is equal to Q plus W. So, this W is equal to 0. There is no heat transfer in free expansion. This also equal to 0. Hence, delta U also will be equal to 0 under constant temperature. And for free expansion of gas, these all things like work, heat, internal energy change, pressure, everything is equal to 0. You just remember it. So, I hope you understood the concept. Then, these equations we have already learned in terms of work done. So, suppose if we are reversing it into the Q in terms of heat, how we can write the equation, that we will see. For isothermal irreversible change, so for irreversible reaction, what is the equation? Minus P external delta V. So, delta V is equal to Vf minus Va. So, in this case, when we are using this delta U is equal to Q plus W, when it is isothermal in the sense, when isothermal means temperature is constant. Okay, temperature delta T is equal to 0. So, delta T when it is equal to 0, delta U, internal energy change also will be equal to 0. Okay. Because actually if we are telling for delta U, another equation is there, Cv delta T. But now, so delta T is 0 means this is a constant. So, delta U also will be constant. But this is specific heat capacity. You have not learned. I will be discussing it later. So, now you think for an isothermal case, delta T is equal to 0, delta U, change in internal energy is also 0. Actually, temperature means what? It is the average kinetic energy. So, when there is no change in temperature means there is no change in internal energy. So, delta T is 0, delta U is 0. So, for an isothermal case, delta U is equal to Q plus W. Since delta U 0, it will become Q is equal to minus W. For an isothermal case, Q is equal to minus W. So, that is written here. For an irreversible change, Q is equal to minus W. So, W for an irreversible, this is for irreversible expansion, minus P delta V. So, since it is minus of W, it will become P external into delta V, that is Vf minus Va. Then for reversible exchange, reversible, it is minus of integral of P external dV. Okay. So, this one we have already derived before. That equation is coming like minus 2.303 nRT log Vf by Va. So, since it is minus W, it will become nRT ln Vf by Va. So, this is the equation for heat. If it is for work, you have to put minus symbol. Okay. Then for adiabatic change, as I already told, you have to know these terms. When you are telling it is adiabatic, adiabatic means what? There is no heat transfer. Q will be equal to 0. Okay. Then delta U will be equal to Q plus W. So, Q is 0. So, it will be equal to W adiabatic. So this is the equation for adiabatic change. And so we have learned the equations for work done, heat, for isothermal, reversible and irreversible. So these equations are very important. You should remember this. For irreversible and for reversible, what are the equations? And for adiabatic, there is no equation you can remember. When you are remembering first law of thermodynamics, you can understand this. When adiabatic means there is no heat transfer, so Q will be equal to 0. So using these equations, we'll see a problem next. Here they have asked 2 liters of an ideal gas at a pressure of 10 atmosphere expands isothermally at 25 degrees Celsius into a vacuum until its total volume is 10 liter. So what I will tell you is, if you are getting some problem, first you have to note down whatever values are given. Then you can easily calculate what they have asked. Okay. So this is an easy way. You should do this. Okay. So here they have asked, here they have given 2 liters of an ideal gas. So volume is given 2 liter. Then at a pressure of 10 atmosphere, pressure is given like 10 atmosphere. Then expands isothermally. So temperature is constant at 25 degrees Celsius. So usually we will be doing the calculations in this will be at Kelvin scale. So we can convert it into Kelvin scale. So 25 plus 273. If you want to convert degree Celsius to Kelvin, you have to add 273. So you will get 298 Kelvin. Okay. Then into a vacuum, it is written, it is getting expanded to a vacuum. Vacuum means it is free expansion. That means P external. This is the internal pressure of gas. External pressure will be equal to 0. There is no pressure until the total volume is 10 liter. So initial volume is 2 liter VI. VF, when it is getting expanded, it is getting expanded to 10 liter. So these are the values given. Using this, we can solve the first part. How much heat is absorbed? So you have to calculate Q. How much heat is getting absorbed and work is done in the expansion. So we need to calculate both Q also, W also. So how we can calculate? So we know in this case which expansion it is, work done is asked. So we know here it is P external is 0. So there is no doubt when it is P external is 0 minus P external delta V. Since P external is 0, W will be 0. Whether it is reversible or irreversible, it doesn't mean. When P external is 0, W will be equal to 0. Since W is equal to 0, what will happen? We can calculate Q. How we can calculate Q? Since so there is no need to calculate again, sorry, there is no need to calculate. This is an example of free expansion. There is no use of any equations, any values here. Everything will be equal to 0 because P external is 0. So there is no doubt. Now let's move to the next question. Here they have asked, so the same expansion but this time against a constant external pressure. Pressure is not 0. Here pressure is 1 atmosphere. In that case, you have to calculate. So, same expansion against a constant external pressure of 1 atmosphere. Okay. So, what we need to do? Same. W is minus P external delta V. Delta V we can write like VF minus VI. Okay. So, minus P external is given like 1 atmosphere. VF final volume is 10 liter minus initial volume is 2 liter. So we will get minus 8 liter atmosphere. So W will be equal to minus 8 liter atmosphere. Then Q, in this case since it is isothermal condition, Q will be equal to minus W and it will be equal to 8 liter atmosphere. It will be just minus of that. Okay. So this much is, it's very easy question. Now let's move to C part. So I hope you have written this A part. I am just erasing it. Otherwise you can write also. There is nothing to write actually. Everything is same only, right? like P external is 0, everything W, Q, everything is 0. So there is nothing to write. So let's move to C part. They have asked 1 mole of an ideal gas conducted reversibly. Now we have discussed about irreversible case. Suppose if it is doing reversibly, what will happen? When you are doing reversibly, W will be equal to minus 2.303 nRT log Vf by Va. Okay, so I have erased the values again. I hope you have written it down. So it will be equal to minus 2.303 N. Number of moles is equal to 1. R you have to take the R is gas constant. R has different values that you should know. Each unit what you need to do that you should know. Like R has different value, like I will write it down here. R is one value is 8.314 joule per Kelvin per mole. Another value is 0.0821 liter atmosphere per mole per Kelvin. So there are different values. Since here we are writing everything in atmosphere and liter, I am taking this value 0.0821. Okay, that value you have to take 0.0821 liter atmosphere per mole per Kelvin into temperature is 298 Kelvin log 10 by 2. Okay. Then when you are calculating, you will get 39.38. W is minus 39.38 liter atmosphere. So this unit also you can see when you are seeing this doesn't have any unit. N is in mole. Okay, this is in mole. R is in liter atmosphere per mole per Kelvin, and temperature is in Kelvin. Log of this value won't be having any unit because Vf and Va will cancel, and since it's logarithmic it won't be having any unit. So K inverse K will get cancel each other, mole and mole inverse will get cancel each other. So work will be having the unit of minus liter atmosphere. Okay, so Q will be equal to minus W, that will be equal to 39.38 liter atmosphere. Okay, so this is the solution. So each case you have to use the equations accordingly. So we'll move to next part, that is enthalpy. So enthalpy is the net heat content of the system. Okay, so as I told, delta U is actually QV. This we have already learned. Delta U is actually QV. How it is coming? Delta U is equal to Q plus W. If this one is carried out at constant volume, what will happen? Q plus W is P delta V. Suppose this delta V is 0. If it is carried out at constant volume, it will be equal to QV. Okay, if this is 0, it will be equal to QV. Similarly, delta H, which is enthalpy, will be equal to QP. How this is coming, we will learn. I will show how it is coming. For now, you should remember H is the net heat content of the system, which is equal to U plus PV, which is a sum of internal energy plus pressure into volume. So this equation also you remember. I will show in the next slide how these equations are coming. But for now, you remember this is the net heat content of the system. H is equal to U plus PV and delta H is QP. These two equations are very important. And another sign convention that I need to tell you is delta H is always less than 0 if exothermic. Exothermic means heat is getting released. In that case, delta H will be negative. If endothermic means heat is getting absorbed. In that case, delta H will be greater than 0. Another thing I need to tell is the difference between delta H and delta U is significant when gases are involved. Okay, delta H and delta U. So we can take delta H and delta U. The different. So if we are taking the difference between them, it is mainly important in when gases are involved. It is negligible for solids and liquids. Usually it is important in the case of gases. So this is just an introduction of enthalpy. So we'll see how these equations give. So for now, most of the reaction will be carrying out under constant pressure. Okay. In that case, we can write like delta U is equal to, as I told, Q plus delta V. Delta U is equal to Q plus W. So I will write first that if it is carrying out at constant pressure, you can write like QP minus P delta V. Okay. W is replaced with minus P delta V. Now, delta U is a state function which we can write like U2 minus U1, final minus initial state, is equal to QP minus P into delta V. We can write like V2 minus V1. It is having a volume of V2 and V1. Now, what we will do is we need to know what is QP. So, we can combine these things, U2 minus P into V2. We can write like U2 plus PV2 minus U1 plus PV1. We can rearrange this equation like this. So now you should remember, before we learned that H is equal to U plus PV enthalpy. That only we can see. This is H2. U2 plus PV2. This is U1 plus PV1, that is H1. That you should remember here. Okay. So we can write it like QP is equal to H2 minus H1, that is delta H. So this only before I told delta H is equal to QP. This is also another important relation that you need to remember. Okay. How this is coming, that derivation I have showed here. I hope you understood. Okay. So here we should know, as I told already, Q is actually a path dependent function. I told in the beginning, state function and path function. Q is actually a path dependent function. But H is a state function. That's why we can write like delta H is equal to H2 minus H1. So why it is happening? U plus PV. In this case, U, internal energy, is a state function, pressure is state function, volume is state function. Hence, H is also a state function. That means QP at constant pressure, heat is also a state function. But otherwise, if no constant pressure term is not there, means Q is a path function. Okay. Now, finite changes at constant pressure is happening. So, if we are taking delta H is equal to U plus PV. So, if we are further deriving something, we can write like, if we are taking the change delta H is equal to delta U plus delta of PV. Okay. So, if it is carrying out at constant pressure, we can write like delta H is equal to delta U plus P delta V. So, this is H is equal to U plus PV. At constant pressure, we can write like delta H is equal to delta U plus P delta V. Suppose it is carrying out at constant volume. Okay, there is delta V is equal to 0. In that case, we can write like delta H is equal to delta U, that is equal to delta U, as I already told, which is equal to QV. Now, one more thing we will learn. From this, how some other equation we can derive. Suppose the reactant and product is there. Okay, this is another reactant A and product B is there. So, for reactant gas, we can write like PVA. According to ideal gas equation, PVA is equal to NaRT. Similarly, PVB for product, we can write like NBRT. What we are doing is we are subtracting PVB product minus reactant PVA, which is equal to NBRT minus NaRT. So, we can write like P of VB minus VA, which is delta V, is equal to NB minus Na, that is delta Ng, that is the difference in number of moles, is into RT. So, P delta V can be written as delta Ng RT. So if we are replacing this equation, that is delta H is equal to delta U plus P delta V, we can write this also like another thing, how delta H is equal to delta U plus delta Ng RT. This is also another important equation. So instead of P delta V, we can replace with the delta Ng RT. So here there are few equations that we need to remember. I will explain once more. One is U is equal to one is H is equal to U plus PV. I wanted to highlight, but actually it is getting dark, and so that equation won't be visible. So I am not doing that. I am just highlighting it here. So one is H is equal to U plus PV. Another is delta H is equal to QP. Another is delta H is equal to delta U plus P delta V. Then delta H is equal to delta U plus delta Ng RT. These are the equations that you need to remember. This is the derivation, how these equations are coming. Okay. So one more problem we will solve. Here again, first we will write down whatever they have given. If water vapor is assumed to be a perfect gas, molar enthalpy change of vaporization, delta H vaporization, molar enthalpy change of vaporization is given as 41 kilojoule per mole. Okay. For 1 mole of gas, so number of mole is given and pressure is given as 1 bar and temperature is given as 100 degrees Celsius. So now itself what I will do, I will convert it into Kelvin. Usually we are calculating everything in Kelvin scale, so I am converting it into, by adding 273, it will become 373 Kelvin. So they have asked calculate the internal energy change. So we need to calculate the delta U when 1 mole is vaporized at 1 bar pressure and 100 degrees Celsius. So delta U we need to calculate. So what equation? We have learned an equation connecting delta H and delta U. What it was? Delta H is equal to delta U plus P delta V. Okay. And also we can write this equation in the form of delta U plus delta Ng RT. So we can calculate delta U. Delta U is equal to delta H minus delta Ng RT. So delta H is given 41 kilojoule. It is in kilojoule. So actually if we are taking R in joule, we should convert it into kilojoule. Otherwise we should convert R into kilojoule. Otherwise delta H to joule. So we need to convert the units before calculating. So R we are taking here in terms of joule. Since delta H is given in joule, we will use R value as joule per Kelvin per mole, 8.314 joule per Kelvin per mole. So we will convert delta H into joule, 41 kilojoule to joule. Kilo, if you want to convert to joule, we have to multiply with 1000. So 41,000 joule per mole. So we will write 41,000 joule per mole. Okay, joule per mole minus delta Ng. So delta Ng we know this is used for 1 mole. It is already told. So since I will tell you one more thing. Usually we will write these units in joule. Okay, delta H, delta U, everything in joule we will write. But here they have given molar enthalpy. Okay, that I will tell you. So since it is given in molar enthalpy, we have to divide everything by number of moles. So that is why it is given in joule per mole. For 1 mole it is given. Okay, so we don't need to include this term here, because this also we are dividing by delta Ng, this also delta Ng, this also delta Ng. Then only it will come in the units of joule per mole. So we don't need to include that number of moles there. Then R is 8.314 joule per Kelvin per mole into T is 373 Kelvin. Okay. So when we are doing this, we will get 37898 joule per mole, which is equal to 37.90 kilojoule per mole. So this is the final answer. Okay. So while doing these calculations, you need to convert the units. That is very, very important. Okay. So let's go to our last topic today, that is heat capacity. So what does heat capacity mean? Heat capacity is the amount of heat required to raise the temperature by 1 degree Celsius or 1 Kelvin. Okay. So heat capacity quantifies the amount of heat absorbed by the system to produce a change in temperature. Suppose we want to rise the temperature by delta T. So how much heat it should absorb? That is defined by heat capacity. So usually the heat capacity will be directly proportional to rise in temperature. Means if we want to rise more temperature, we need to increase the heat. Okay. So heat transfer means rise in temperature. Right. If you are heating something means there will be an increase in temperature. So that increase of temperature is actually directly proportional to the heat transferred. Okay. So this heat transferred is directly proportional to the temperature difference. So to change this proportionality sign, we can multiply with a proportionality constant, that is C. So which is called the heat capacity. So here the C is called the heat capacity. So the value of C depends on system size, composition and nature. So it varies. This heat capacity varies for every substance. Okay. So there are two different categories of heat capacity, molar heat capacity and specific heat capacity. Molar heat capacity means it is the heat required to raise the temperature for 1 mole of a substance. Actually, heat capacity is the heat required to raise the temperature. So, if it is raised for 1 mole of a substance by 1 degree Celsius or 1 Kelvin, that is called molar heat capacity. So, we can write it like molar heat capacity Cm, which is equal to heat capacity C by N. We can write it like that. Okay. Then, specific heat capacity. So, specific heat capacity means it is a heat required to raise the temperature of 1 unit mass. So, this change only here it is happening. Here it is for 1 mole, here it is for 1 unit mass by 1 degree Celsius or 1 Kelvin, that is called specific heat capacity. So, in this case, specific heat capacity, we can represent it like by small c. Okay, otherwise Cs, whatever you want you can represent. So, we can write it like C by heat capacity by mass. This is a unit mass. Okay. So, we can again write it like specific heat capacity is equal to heat capacity into mass. Okay. So, Q, as I already told, it is equal to C delta T. So, we can write it like Q is equal to C into M into delta T. We can write it in any form. So, you don't need to remember all these equations. You need to remember what does that molar heat capacity means. It is by heat capacity by number of moles. It is for 1 mole. And specific heat capacity is for 1 unit mass. That's why C by M. And you need to remember this equation Q is equal to C delta T. So, we know heat is directly proportional to the temperature rise. So, suppose you see here two things are there. One is having a specific heat capacity of 1007 joule per Kelvin kilogram and another is 4183. So, in this case, this substance is having higher specific heat. Okay, so this one is having higher specific heat. So, in that case, what does that mean? When specific heat is higher means it requires more heat to rise the temperature. Okay. When this one is more means it requires more heat to rise the temperature. That means it won't heat up so quickly. When the heat capacity is less, it will heat up very easily because it requires less energy to rise the temperature so that it will heat up quickly. So that is a practical application you can think of. You have taken two substances, water is having this much specific heat capacity and another some oil or something is having this much heat capacity. So, which one is getting heated faster? So, based on that, you can tell which one is having higher heat capacity. So that is a practical example that you can think of. So now you can think and tell water or oil is having higher heat capacity. You take same amount of water and same amount of oil and try to heat it. Which one is getting heated faster? So which one will be having higher heat capacity? You can think and drop in the comment section. So let's see how good you understood. So finally we will move to a derivation. So this is also another important, very important equation, Cp minus Cv equal to R. This you have to use at different places. So how this relation is coming? Cp means heat capacity at constant pressure, Cv is heat capacity at constant volume. So how this is coming? For this, as I told, we have already learned delta U, which is equal to Qv. Another we have learned delta H is equal to Qp. These two things we already learned. So, we know what we know. Q is equal to C delta T. That we have seen just before this. So, we can write it like instead of C, it is at constant volume. So, Cv delta T. Here, since it is at constant pressure, it is equal to Cp delta T. So, we got delta U and delta H. Another thing what we know, delta H, another equation we have learned, delta H is equal to delta U. So, we have to connect these two. Delta H is equal to delta U plus P delta V. Okay, otherwise we can write it like delta H is equal to delta U plus R delta T. For 1 mole of gas we can write like R delta T. So, this is another equation. So, delta H we can replace with Cp delta T. Delta U we can replace with Cv delta T plus R delta T. So, if we are dividing by delta T, everywhere delta T is there. So, it will become Cp is equal to Cv plus R. That means Cp minus Cv is equal to R. This is another important equation. So, here you have to remember this equation, Cp minus Cv is equal to R. Another equation is delta U. As I told, it is equal to Qv, and also one more relation, Cv delta T. So, from here only before I told, if you are remembering, under isothermal condition, suppose if delta T is equal to 0, if delta T is 0 means since this is a constant, this also will be equal to 0. This I told before. I hope you remember. Okay. Another important equation is delta H is equal to Qp Cp delta T. So, these three equations you have to remember. Okay. So, let's stop here. We will continue in the next class with the remaining portion. I hope you understood this session. If you have any doubts, please comment below and see you soon.